everyone. I am absolutely delighted to announce that we have an astronomy colloquium by our guest speaker, Professor Karen Masters. I got to know her work right when I started grad school. It's all about spiral galaxies, which is the thing that I started researching. So I've been following you for about 20 years in scientific writing. So I'm excited to hear the talk today. She gave a fantastic, completely unrelated talk at the Bullet Lecture yesterday. If you missed it, hopefully we'll have a YouTube up soon. But it also comes with a wonderful book about all the books in astronomy that shaped our universe. So I was very, very happy, and I think so was the audience, since they bought your book in fair numbers. Yeah. So yeah. Okay, so without further ado, I'm absolutely thrilled to present to you Professor Karen Masters from Haverford College. So,
can you all hear me fine if I talk like this, or does anyone want the microphone?
It's really bad. I couldn't use that. The acoustics are horrible.
So I can use a microphone, and then everyone can definitely hear. And if I get tired, just shout at me, okay? Okay, cool. So I'm pleased to come and talk about spirals and galaxies. Ben was the first person I ever met at a conference that came up to me and said, I read your paper, can we talk about it? I don't know if you knew that, but it's true.
Okay.
That was a paper about dust in galaxies. So some of you I know are here working on that very topic still. Most generally, I'm just interested in galaxies in general, and in particular, find spiral galaxies really interesting. I had the pleasure of having a sabbatical. I think it was the spring of 2021, so I spent it in my basement, but I got to work on this annual review paper with Jerry Selwood, who's a dynamicist who works on dynamics of disk galaxies, and it was like my own private set of lessons on the dynamics of spiral galaxies. And so I've developed this talk with, I'm mostly an observational astronomer, so it has a lot of reflections on what contributions my group has made to understanding spiral galaxies, but also a little bit of an introduction to the interesting dynamical physics and other stuff going on in spiral galaxies. So I find the history kind of interesting. Those of you who were there yesterday probably can guess that. And so I'd just like to start with a reflection that we've known about spirals and galaxies for, coming up for 200 years now. So this guy, Lord Rosse, built a big telescope in Ireland and observed a bunch of galaxies and published some of the first illustrations of spirals and galaxies. So this is the Whirlpool Galaxy, which is a nearby big galaxy. It's kind of in the Big Dipper. So it's a nice target. And you can see what a great job Lord Rosse did. This is a HST image of the same object showing this beautiful spiral structure. And you really have a lot of similarities. One thing I learned through studying spirals, though, which I always find interesting, is that this swirl in Vincent van Gogh's Starry Night was inspired by this drawing from Lord Rosse that Van Gogh had apparently seen. I don't think, you don't kind of immediately jump to galaxy when you see this, but I think when you see the two next to each other, it seems very plausible, right? So these are beautiful objects, but they're also really fascinating physical objects. So let's learn a bit about them. If you've ever taken an astronomy class, you've probably learned about the Hubble tuning fork, the classification scheme for galaxies. So Edwin Hubble in the 1920s sat and looked at a few thousand photographic images of galaxies. These would have been negative, single filter, no colors. And apparently he smoked his pipe when he did this. So here he is looking at an image of a galaxy. And he published a classification scheme, which he later described as a tuning fork with the kind of two main parts of types of galaxies on either side. So we have these elliptical galaxies, which are smooth and featureless. And then we have the spiral galaxies, where they're really distinguished by seeing these spiral structures. Hubble also noted that there are differences between spiral galaxies in particular. There's some differences with ellipticals, but mostly it's about the shape, so they're classified by shape. And we won't really talk about ellipticals again. But the spirals have a number of different differences. So in particular, he ordered them by how tightly wound the arms are. So you can see they're kind of more loosely sort of open and tighter here. He noted that correlated with how large the central light was. So you have bigger central light concentrations. And also some concentration with how smooth the arms are. So these are very, very smooth arms, and these tend to be patchy. And then he did this in two branches. Where there was one branch where the spirals start right from the center, and another branch where they start from the ends of something he called a bar, like an iron bar, so just a linear structure of stars. And most sort of I guess you guys call it Physics 107, I've learned. We call it Astro 101. Most people who take that kind of class learn about this, and it's in every textbook. So that's something we need to know. Probably many of you are familiar with it, but if you're not, I wanted to make sure we talked it over. A little aside from my book. This is a little extra thing for you all if you're interested. So this was a book that was published 50 years before Edwin Hubble did all that classification. So this is Richard Proctor, who wrote a bunch of books for popular audience about astronomy. And I was super surprised to note a chapter in his book from 1870 about if nebulae are external galaxies or not. So some of you may know there are these catalogs of things that are fuzzy, that might mistake you into thinking they're comets, or were generally called nebulae. They're not points of light like the stars. If you look at them, they're kind of fuzzy. And there was this huge debate about what they were and if they were things inside our galaxy or other galaxies. As Richard Proctor, is noting. He would have seen this, right? This is from before 1870, and he had seen other things. But I was really surprised. This is his little cartoon of the structure of the galaxy that we live in. So this, to me, seems quite early for that to be in a popular science book, which is cool. And he also is noting that the reader can see, so this is popular science readers in 1870, how spectroscopy can tell you what something's made of in space. So we'll come back to this idea that spectroscopy is a really useful tool for astronomy. We can learn a lot about what's going on in galaxies by taking spectra of them. And so he's suggesting you could figure out what the galaxies are made of, if they're made of stars, so they're like galaxies like our own that are made of stars, or if there's something in our galaxy that's made of something different. So I just thought that was really neat, and it's a little aside. Okay, back to the main story though. So we've learned about the Hubble tuning fork. That's our kind of bulk classification. There's other ways in which spirals differ. So this was a version of it from de Vaucouleurs in the 1950s, where he kind of added another dimension. It's like he took the Hubble tuning fork and like rotated it. And he said, it's barred and unbarred, but it's also whether or not they have these rings. So you can see, here's an example, a galaxy with a really nice little ring around the end of its bar. Here's another one with a ring around it. The ringed ones are on this side, right? Here you've got ringed ones, but no bars. And then you've got bars, but no rings, and no bars or rings. So there's lots of diversity, basically, is my point, in how spirals look in the universe. And that's something we'd like to understand in any kind of physical model of what these are. And then there is this distinction that Deborah Almagren led the development of in the 1980s between flocculent and grand design spirals. So our friend, the Whirlpool galaxy, is the prototypical grand design spiral. You can trace the spiral arms over the entire range of radii, and they're very coherent, they're very connected. They're like these little, almost like a little superhighway, right? So that's our grand design, very, very large-scale spirals. And then you have flocculent spirals, where it's clearly spirally, right? And you can kind of trace little segments of spiral, but you can't trace any one spiral over a large range of the disk. And flocculent, well, I wrote it here. It's a word that means sort of fleece-like or fluffy. So these are our fluffy spirals. And not all spirals are either this or this. There's some intermediate types. But it's another kind of type of diversity of spirals that we'd like to try to understand. Okay, right. And so to finish the tour of spirals in the universe, it's not just galaxies that have spirals. There's spirals all over the place in other dynamical systems. So for example, protoplanetary disks often show spirals. So this is a region in our galaxy. It is a nebula in our galaxy that is forming stars. And if you zoom right in with the ALMA telescope, you can see the cold dust in a disk around a new star. And you can see that there are spiral features in this. The rings of Saturn are actually spirals. I wouldn't like to have the job of tracing them around, but if you trace them around, they're not complete rings. They're actually very, very tight spirals. Hurricanes have spirals features, typically, and you can make your own little spiral by stirring cream in a coffee cup. There's a really charming paper that the appendix of it tells you how to make spirals in coffee cups and in saucepans and things and like simulate them for yourself. Okay, so spirals are all over the place and they clearly have something to do with dynamics. So let's learn a little bit about the sort of mathematical description of spirals, and then we'll get on to the physics of what they are. So it turns out spirals in galaxies are mostly something called a log spiral. And you see log spirals all over the place in nature. This is a Mandelbrot set with a log spiral. I guess that's not nature, but it's mathematical. Some shells and other things like that have this log spiral thing. The feature that makes a log spiral special is that its pitch angle is constant with radius. So we need to know what a pitch angle is. So pitch angle is just the angle between the spiral and a circle at the same radius. So here I've got my mathematical spiral, the blue, and the gray in the background is a bunch of concentric rings. And so at any radius, you're calculating what is the angle between the tangent to the circle and the tangent to the spiral. This is your, and then if you have a log spiral, this is a description to plot this line. R is just this constant thing with pitch angle being a constant with radius. Okay, so here's the user participation. Large pitch angles are very open spirals. Okay, so what shape has a 0 pitch angle? Have we been listening? You can do it. Go ahead.
Circle.
Exactly. What shape has 90-degree pitch angle?
A line.
Say what?
A line. A line.
A line. Yeah, that's like the spokes on a bicycle. Or 90 degrees. And bigger than 90 it's just backwards. And so we only go between 0 and 90 for pitch angles. Okay, and then one other concept we need, right? This is a static image. I should have made a version that's a GIF or something. But we also use this concept of pattern speed in spiral galaxies a lot. So the pattern speed would be if I was rotating this, it would be the angular speed that I'm rotating the spiral. This becomes important because it's not the same as the speed at which the stars are going in the galaxy, as we'll see. And in fact, I think the next slide explains why that is the case. That was the first model, right? That the spiral arms are just made of stars. They're kind of like a ribbon. And so you're just seeing where the stars are in a galaxy. And then if you followed it over time, what would happen? So one thing we know about galaxies from observing them with spectra, with getting the Doppler shift from spectral measurements, is that they rotate differentially. So the circular velocity of a typical galaxy, once you get outside some particular range, is pretty flat with radius. That means, but the things that are further out have further to go, right? The circumference is larger. So that means the outer stars would end up kind of trailing the inner stars. And we end up, if you had a material arm, like in this simulation, they would wind up quite quickly, actually, in just a few galaxy rotations. And so there's this initial kind of description or initial kind of problem you encounter when you start to learn about the physics of spirals in galaxies. It's called the winding problem. Spiral arms cannot be material arms, can't be just made up of where the stars are, because if they were, they'd disappear very quickly. They'd wind up, and then you wouldn't see them anymore, because we're starting now to look like concentric circles rather than a spiral.
What's its typical spin around time? That's kind of relevant, I guess.
No, it is relevant. It's now, that's a number I really ought to know. I think it's like 250,000 years for the Milky Way. I think that's what I remember. Or is it 25 million years? I think it's 25 million years for the Milky Way.
Which is still small.
Which is a long time. Yeah, exactly. It's large, but small compared to the age of the universe. There's a really neat comparison of it to the timescale for the dinosaurs. And so this idea that, you know, if you go back in time to when the dinosaurs were, the sun was actually around the other side of the Milky Way, which is kind of pleasing somehow. I don't know. I find that pleasing. Okay. So this winding problem led to the development of the idea that spirals in galaxies must be density waves. So that means they're not made up of the same star always, but they're just a region in the galaxy where there's more stars collected together. And stars will pass through them as they go on their orbits, but there's like this sort of collection of them. So the best kind of illustration of how this works is this cool traffic jam movie that was made in Japan, I think a long time ago, but it does a great job. Doesn't have a date, which is a shame. So what you're going to see is the cars going around initially at pretty much constant speeds. In fact, they mostly stay at pretty constant speeds. But what ends up happening, and they slow down the movie, is you get this patch where they're much closer together. You may have experienced this on the highway, those traffic jams which you don't really understand why they're there, where you just suddenly you're in a denser part of stars. So this is an example of a density wave, right? An individual car is not staying with the pattern. The pattern is here. And the pattern has an angular speed that it's moving around. That's our pattern speed. And the cars are going at a completely different speed. Okay, so a spiral galaxy doesn't look like a single ring of cars, but you could model it as a bunch of concentric rings of stars. And if you had all of these traffic jams going on together, in the stars, it would look like a giant mess, except that those overdense places where there's more stars have a little bit of gravitational pull. So over the time scale of a galaxy, they get lined up. And these little traffic jams, the little overdense regions, the pattern speed gets lined up in this spiral, and you end up with a spiral structure. It's pretty neat, right? The thing about it, though, is that to get it to happen, you need some kind of triggering, typically. And so we think we see that in a lot of galaxies. We think, the whirlpool has this little companion galaxy, and so its beautiful large-scale structure of spirals may well be triggered by that companion. Many galaxies have dwarf companions that could be triggering their spiral structure. So that's one way it could happen. There's a lot of papers about how these galactic bars might trigger spirals. So a galactic bar is actually another kind of dynamical feature. It's kind of a way of the galaxy not completely collapsing in on itself due to gravity, and then there's angular momentum, so you end up with this kind of line that's to do with the balance between wanting to collapse into a sphere under gravity and angular momentum not letting you do that. But once you've set up the bar, you've got this large-scale kind of stirring thing going on in the galaxy, and you get spirals coming out of the end of it. The other thing that's kind of interesting to note, that the physics says that these density wave spirals should always trail. And it turns out this is a charmingly difficult measurement to make, such that we've actually only ever measured it in like a few hundred galaxies. Which in sort of the modern era of galaxy evolution kind of blows your mind. We have catalogs of millions of galaxies, thousands, hundreds of thousands of spirals, but we've measured this in like 100. That's because you have to look at each image to figure out which is the near side and which is the far side. Turns out the dynamics is really easy to get, like in this galaxy, this side is moving towards us, this side is moving away from us relative to the center. That's pretty straightforward to do for galaxies. We do a lot of spectroscopy. But then you got to sit and look at it and figure out that this is a dust lane. That means this bit must be in the foreground. So this is the front. So it's rotating this way. So the arms are trailing. And so it's de Vaucouleurs again in the 1950s did this for 17 galaxies and made these beautiful illustrations where he decided which way the galaxies were tilted. In the 1920s, Slipher did it, and then there was some work in the 1980s, but I haven't seen any more recent work on this. Perhaps because basically all of them are trailing. So the spirals, they're log spirals that are consistent with being density waves in basically every galaxy that we've looked at. Okay, but the universe is a big place, and there are pretty isolated spirals that don't have a bar. So that's a puzzle. Actually, this is M101 is not that isolated, but it looks pretty isolated in this image, and I enjoy showing it. It's an image taken by an amateur astronomer who's been involved in Galaxy Zoo. And the other thing is that in simulations of isolated galaxies, spirals develop. So in computer simulations that include the right setup, you get spirals developing, even if you don't have a companion and you don't have a bar. So you must be able to make spirals even without these features. And the other thing you might notice about this simulation, is that, and it says it in the title, it actually is a winding spiral. It's winding up in the center, and then it's sort of reforming in the outskirts. So at all times you see a spiral, but the exact details of which spiral you see at any moment kind of come and go. These are called transient winding spirals. So we've kind of, we do think that many spirals are density waves, but as a field, the dynamics has moved on to considering how to explain this, and that not all spirals may be these simple density waves. And it is actually okay to have winding spirals, we think. And so Jerry, my collaborator on the paper, is very excited about this model, and we spent a lot of time trying to talk about what this model was. He calls it the self-excited instabilities. And they're basically, the spirals end up being kind of waves. They are still density waves, but they're kind of more complicated self-excited density waves in the disk of a spiral. And so here's an image from one of his papers showing the sort of the density wave that turns out to get set up as a spiral. You can think about this in a few different ways. I kind of like to think about it in intro physics type language, where you think about waves coming through features, you end up with constructive and destructive interference between waves. So you can end up with kind of structures which are there because of the overlap of the waves that you see going on. So another way to kind of think about it is I don't know if you've ever seen these music videos from Semantics, but they do all kinds of cool little physics experiments with their music. And so they have sand on these plates and they're playing music at them and they come up with all these different weird shapes because of the way the resonant modes overlap. So you're like, what does this have to do with the spiral galaxy? Well, spiral galaxy does have edges, right? It has an edge where it runs out of stars. It has a center. It's also rotating, so it has some frequencies that are kind of integral to it, at least, but that changes as a function of radius. It's kind of a complicated system, but you kind of can see how you can end up with resonances overlapping and you end up with spirals. And particularly, perhaps, flocculent spirals, the kind of patchy ones, maybe, this kind of spiral. Okay, so here's a list of things that I have tried to tell you about spiral arms, and a list of questions which I think they raise. So spiral arms are probably mostly density waves in the stars in a galaxy, but they're probably not static. So if you've ever heard of the Lin and Xu density wave model, it's probably not as simple as that. And the density waves, for the most part, require some kind of driving. There is, however, some evidence for spiral arms winding up in galaxies. So I showed you from simulations, but there's some evidence observationally, actually, that they might fit this model of winding up. I jumped ahead to the links to tides and bars. But how are we explaining spirals in isolated galaxies? That remains a little bit of a puzzle still. Is any galaxy in the universe really isolated? I think is an interesting question to ask. And then we haven't really talked about this at all, but do these matter at all? Do they have any impact on galaxy evolution? Like, are they just like pretty things that we like looking at, that are like frosting on a cake? Or are they something that's integral to the evolution of galaxies? And I find that question interesting. And if you look at the Whirlpool galaxy, you can kind of see that the dust is lined up with the spiral, and all of this pink stuff, which is hydrogen alpha emission, is lined up with the spiral. So you can see at least, the galaxy is organizing itself so that the spirals seem to be impacting it on local scale. But does the fact that this galaxy have these spirals change how it evolves over very long timescales? Is interesting to me. Okay, so I like to try and understand this stuff observationally and using big surveys. So I want to tell you a little bit about the Sloan Digital Sky Survey. I see you have one of the plates in the planetarium, which is cool. This is a project I've worked with for a pretty long time. At this point, it's been running since before I finished my PhD, but I did use early data from it. And I've been very involved in it for the last sort of 10 years or so. It uses a pretty small telescope in New Mexico, and it was pretty efficient survey observing, so it made images of a third of the entire sky, spectra from a million galaxies. So once you have a spectra of a galaxy, you can have a distance to it, and you can make measurements of various physical properties, and all kinds of useful stuff. Okay, so I want to understand galaxies better, and this is the big data version. I'm not going to sit like de Vaucouleurs and draw a picture of all of them. So how am I going to do this? The thing is, everyone always just says just throw a machine at it. Just throw a computer algorithm at it. So this is my slide to try to explain why we don't immediately just jump at throwing a computer algorithm at it. Galaxies are complicated looking, patchy, they have foreground stars, they have image artifacts. So historically, and even today, it is a hard machine learning problem. It is a hard problem. It is just as hard as it is to distinguish, if you're a machine, between puppies and bagels, or puppies and loaves of bread, or to tell if you're a robot, you could identify the spiral galaxy in this image. Kind of says something about how hard it is to do, right? And actually none of these are spiral galaxies, they're all computer generated, which bugs me, but that's life. Okay, so we're not gonna just, people try, right? So people really try hard to do it just with machines, but we're not just gonna jump there. Instead, we're gonna try and do it with people. So we're gonna try and do it with crowdsourcing, with Galaxy Zoo, which is another project I've been involved with for a long time now. So it's been going for 17 years. Oof. And it started to try to classify and to identify spiral features and other image other features and images of galaxies from the 1 million galaxies I mentioned in the Sloan Digital Sky Survey. But we've kind of just moved on, and now we do all kinds of surveys. So we've also done lots of surveys of galaxies from HST. UKIDS is an infrared telescope, a survey project that ran for a while. DECLS is using the 4-meter Mael telescope, so it's somewhat deeper imaging and has also southern hemisphere imaging, so it's a much bigger area. So we actually have 8.7 million galaxies with classifications in that one. And with Zubot in the loop, so with the machine learning helping us, which we might get to. And we've done some classification of simulations of galaxies as well. We keep going, so here is some information about what Galaxy Zoo is doing now. So one of the things I talked with Ben about while I was here was the Galaxy Zoo catalog for the Gamma survey, which Ben has been working on with a number of students. We have some JWST images on the site, so everyone wants to look at JWST images. We're still working on getting more up, but we've processed about 8,000 through the project, and some other surveys. Euclid has been a really big collaboration for us and is going really well. We're part of the Euclid pipeline for galaxy morphology, which is cool. So Euclid is a space mission out of ESA, and they have Galaxy Zoo as part of their formal procedures for finding galaxy morphology. Yeah, so we're doing all kinds of stuff with Galaxy Zoo still, even though we've been going for 17 years, so that's good. So what is Galaxy Zoo? I don't know, does everyone know already what Galaxy Zoo is? You kind of many of you work with Ben, so you know what it is? Yeah, but you still want to hear the history of how it started? Yeah. Okay. Most people do, so it's cool. Okay, so back in 2007 or so, when Sloan put out the 1 million galaxies, people wanted to figure out how to classify them. And so this is before I was involved in Galaxy Zoo. Some of my colleagues were at a pub in Oxford, and were talking about this problem, and realized that they could ask people, and they were like, well, how about we put this on a computer in the break room of the physics department at Oxford, and people can come by and classify it on their break. And then another colleague was there and was like, wait a second, what if we made it a website and we just ask anyone to do it? And if we're going to ask anyone to do it, we want to make the questions kind of simple. We want people not to have had to take Astro 101 before they can do this. We want just anyone to be able to do it. And so it launched with this as the training. This is a spiral galaxy. This is an elliptical galaxy. Go. So we got it. And it turns out, the images we show are a little bit more complicated than this. Sometimes they're more ambiguous. But the very first phase of Galaxy Zoo was very simple, just spiral or elliptical. And it was really, really popular. So this is July 2007. It was on the front page of the BBC website. And it was the second most emailed story for a little while. It was only less interesting than a man flying to a wedding a year early. I don't know why. And then this is the classifications per hour in the first day and a half or so after the site launched. So it launched presumably in the morning in the UK, and then after a few hours, Americans wake up, I think, and it's in the press and stuff, and you get this huge spike. But look at this, it goes up to 40,000 classifications an hour. So it kind of went viral, basically. It was a really popular project, and a lot of people classified in it. The initial hope stated in this article is that about 30,000 people might take part in the project. There's 1 million galaxies. You probably want to collect a couple of classifications per galaxy to make sure that things aren't wrong. So the thought was it would take a few years to do that with 30,000 people, and that's fine. It would take a while, but at least we could get it done. All of them were classified 40 times in about 18 months. So they got 40 million classifications in 18 months. And it worked really well. So this is when I started to join the project. I came along in October 2008 and was a new postdoc at Portsmouth at that moment. It was my second postdoc. Wanted some new projects and got involved with Galaxy Zoo and wrote some of the early science papers. We always thank our volunteers. So every paper has this acknowledgement that says we are made possible by the participation of some number of volunteers. Usually we track the phases, so the number sometimes changes, sometimes it goes up, sometimes it goes down, because we're tracking who contributed to a specific set of classifications. And you can also go on the web and see names scrolling by of people who wanted to have their names there. The very first paper, my colleagues did try to submit it with 100,000 authors, but the journal said that wasn't appropriate. So we don't do that. Only if volunteers are contributing very directly to the text of the paper do they become co-authors, and that happens sometimes. Otherwise, they have an acknowledgement thanking them for classifications. So this is what a Galaxy Zoo classification looks like. So I mentioned the very first version was very simple. Since it worked really well, we realized we could ask more complicated questions. And so we went back. So that was GZ1 was the first version. This is GZ2, which was the same survey, the same Sloan survey. We used the brightest, biggest in angular scale galaxies, so it turns out to about 250,000 of them, but asked more complicated questions. So here's a galaxy that is its classic morphology is that it is a spiral galaxy with a bar. It has some evidence of a ring, and it's an AB galaxy, so it's kind of intermediate. What did Galaxy Zoo say? Well, 39.019 people classified this galaxy. So what does that mean? A thing got involved?
No thing from the Adams family?
Yeah. I mean, people come in integer numbers, but what we do is we actually go through and run an algorithm that looks for people who consistently disagree with everyone else. So this can happen for a variety of reasons. Someone misunderstands the task. Some school kid thinks they're going to mess with us. I don't know. I can't think of any other reasons. Come up with the reasons why someone might consistently disagree with everyone. If you occasionally disagree, whatever, that's fine. But if you consistently disagree, we're going to downweight your classifications. And so you end up with fractional numbers of people because we apply these down weightings. Usually, most people's weighting is very close to 1. So usually, most people are contributing all of their classifications. We're just looking for the rare cases of things going wrong. Let's just say this is 39. So of our 39 people, 38 saw a disk here. Okay, so there's always one, but with 38 out of 39 people saying they see a disk, we're really confident there's a disk in this galaxy. The vote fractions tell you what's in the image, typically, once you get to large enough number of people. 37 of the 38 said it's face on, which again, I would agree with. So again, there's always one, fine. But we're really confident this is a face on disk galaxy now. We're pretty confident this has a bar and has spiral arms. They're medium spiral arms, so that's pretty good, right? It's a medium galaxy. We're pretty confident it's got 2 arms. This gets a little harder, and all these other things. And so you get these vote fractions, basically, for each of the morphological features. Because it's a tree of questions, the numbers of people answering later questions sometimes get kind of small, but you can still do statistics with it. So just a reminder, the physics we're testing when we're looking at galaxy morphology, it has to do with the orbits of stars. So spiral galaxies have to have a disk of orbiting stars. That's why you get spiral features and spiral structure. Elliptical galaxies are more random in their motions. So there's some real underlying physics we're testing with galaxy morphology. It's not the only information you get about a galaxy, though. So a reminder about the fact that galaxies are made of stars, and some work. I wanted a big shout out to Beatrice Tinsley for this. This idea that if you take the color of a galaxy, you can understand the types of stars that are in the galaxy. So you remember stars come in all different kinds of colors, and the brightest stars are blue, and are many, many orders of magnitude brighter. This is a log scale. Many, many orders of magnitude brighter than the red stars. The other thing, though, about these blue stars is they have very, very short lifetimes. So this is 10 to the 7 years compared to 10 to the 11 years. So if you have a gas cloud in a galaxy forming stars, initially it forms stars of all colors. The blue stars completely outshine everything, and that gas cloud's going to look blue. But then pretty quickly, the blue stars go supernova, make the black holes and stuff, do interesting things, and then what's left is red stars. So if you see a population of stars that looks blue, you know it's young. If you see a population of stars that looks red, you know, for the most part, it's old. The complicating factor is dust, of course. It always is. But to first order, the color of a galaxy tells you the age of the stars in it. Okay, so it turns out that most elliptical galaxies, I've put bulge early here, but like galaxies with that elliptical sort of spherical thing, or spirals with big bulges, tend to look red. And most of the spiral galaxies look pretty blue. And this is in every textbook. Spirals are blue, ellipticals are red. And then this is your textbook explanation of what goes on in galaxy evolution. Your blue disk galaxies merge, they have an AGN and a starburst, and you're left with a gas poor elliptical after this all happens. And then the other thing that's interesting, this happens more often where there's more galaxies, so there's more elliptical galaxies in clusters, which is true as well. However, this picture is not quite true. There's a number of little problems with it. For example, when you have just two things merge, you end up with a lot of angular momentum left over, so you end up with a rotating disk typically. They quite often don't get rid of all of their gas. Sometimes they do. There's a lot of details, basically, that don't quite work. And Galaxy Zoo kind of contributed to this idea that there's details here that we're not capturing by pointing out there's actually quite a lot of red spirals, and there's even a few blue ellipticals. So we've had a number of papers using Galaxy Zoo morphologies up until just a couple of years ago, but over the last decade or so, pointing this out. So these are things called color magnitude diagrams or color mass diagrams for galaxies. So color correlates with the mass of a galaxy. So more massive galaxies are redder. And if you do like the little contour diagram of where the points are, you see there's kind of two populations. There's this sort of red sequence and a blue cloud, with a gap in the middle that gets called the green valley. And so the majority of textbooks and a lot of astronomers still will associate this red sequence with elliptical galaxies and this blue cloud with spiral galaxies. If you go ahead and put just your elliptical galaxies and just your spiral galaxies, early and late here are just other terminology for elliptical and spiral. Apologies for not changing that. You do see that there is a trend there, right? You know, when you plot the ellipticals, you mostly have red sequence with this little tail into the blue. What's interesting is when you plot the spirals, you know, you really don't see, you see a lot of them are blue, and the locus of the population is blue, but this huge tail to red spirals. So I found these interesting over the years. You can see that's me in 2010 writing about them. They're kind of interesting things. They really do just have spiral structure, but they look red. This is obviously an edge on dust red one. And here are some blue ellipticals. Oh yes, and then one of our lovely volunteers, before Twitter went to whatever it is now, has this cool tweet that she has ellipticals are red, spirals are blue, at least so we thought until Galaxy Zoo, which is quite charming and oversimplified. Other people had pointed this out before, but we did it with a lot of big statistics, and we keep doing it, I think mostly because people keep using red to pick ellipticals. And so here was this 2022 paper where we did histograms again of the color of ellipticals and spirals, pointing out if you just do the color cut to pick out ellipticals, you're going to have contaminated samples. Does this matter? Well, maybe a bit, especially if you are trying to learn about like the assembly of galaxies and how much angular momentum a galaxy has. If you're picking galaxy populations on color, you're picking like a mixture of angular momentum populations. Yeah, and red spirals are cool. And so we go from everyone loves a cartoon, right? This traditional kind of textbook picture that maybe you need to have a phase where you fade to a red spiral before you can turn into an elliptical. And also the Milky Way might be a red spiral. So we all like to learn about the types of thing we live in, right? It's pretty hard to measure the color of the Milky Way because we're in the middle of it. And so you have to kind of estimate what the color would look like based on what we know about star formation rates and stuff. And so the estimates tend to put it kind of in the green valley. But maybe it's a red galaxy. All right, let me check the time. Okay, so we want to learn a bit more about spirals. And so I want to just remind you a little bit about this classic spiral sequence that Hubble put together, where he calls spirals SA to B to C on the basis of a few different things, including how tightly wound the arms are and the size of the central bulge. And historically, as kind of described here from Ron Bucher in 2012, historically the windiness of the arms is what like set the type. And so you find people talking about SC galaxies with large bulges, or SA galaxies, which are loosely wound arms. You find that in the literature. They're rarer objects, but you do find people saying it's the windiness of the arms which sets this sequence. So reminder again about pitch angles. We're going to go ahead and try to estimate these pitch angles. We're going to kind of do it with Galaxy Zoo the way that Hubble did it. Rather than measuring an actual angle, which turns out to be pretty hard to do with these patchy arms and stuff, it's one of the I think, hardest problems in understanding spirals. We're going to just use a more qualitative description, a Galaxy Zoo question. Are they tightly wound, are they medium, or are they loose? And again, we're doing this in a crowdsourcing way, so we have lots of answers to this. So we get pretty nice, reliable answers. And we actually turned those answers into a single number, which we call the windiness, which is 1 if everyone says the arms are tightly wound, and is 0 if everyone says they're loosely wound, and goes in between those numbers if you get different answers. And then we can also come up with a score to do with how big the bulge is. Lots of different ways to measure this, but this happens to be using Galaxy Zoo votes, which correlates pretty well with others. And what we found, you should, since Hubble said there's this sequence, and you have big bulges and tightly wound, and little bulges and loosely wound, it should correlate in some way, right? It does not correlate. So this was some work I did in 2019. This is almost 5,000 spirals in a volume-limited sample from SDSS, and this is what we found. You don't tend to get things with large bulges that are very loosely wound, but you get things with small bulges across an entire range of arm windiness, and there's no strong correlation in either direction between these two properties. So statistically, there's no correlation.
Is there an implicit assumption that these are kind of steady in a dynamical sense? In other words, you don't have time as one of your, or how old they are as one of your axes?
Well, that's a really interesting question, right? So it's always more complicated with galaxies. So the next thing we did was look at this by color, and look at this by the age of the stars in them. Okay. So it's an attempt to put time in it. And you find that it's a little bit more complicated if you look particularly at low mass blue galaxies, which are the kind of galaxies that would have dominated the sample that Hubble used. You do find a correlation. It's not a super strong correlation, but there is a correlation. In higher mass and redder spirals, there's an anti-correlation. So if you put that population together, you kind of wipe out the correlation. So there's something interesting here. I still don't really understand this. I think it's really interesting. This was work by Petra Mengistu, who just graduated from Harvard last year and has just started a PhD at Santa Cruz. And we did one of these, it got published in the research notes, and we did a little YouTube video that AAS sometimes do with the authors. It was pretty fun. All right, in the last few minutes, I just want to talk about the impact spirals might have on galaxies and how we might try and test that, and how some students in my group have been working on that. So if most spirals are density waves. If they're density waves, they should have impact on star formation in the galaxy. Either you have more star formation in the arms just because there's more gas in the arms, because the gas also is denser there, and if you have more gas, you have more star formation, or the density wave going through the gas also additionally adds shocks to the gas and helps the process of star formation be more efficient. And there's some really charming illustrations of this happening, and you can see as the spiral density wave passes through the galaxy, you should have the youngest stars on the density wave and then slightly older stars moving away from it. And people try to look for this. So it's beautiful work by Yu and Ho in 2018, looking at this one galaxy imaged in different filters that pick up younger or older stars. And you can see that there's a sort of consistent, the youngest stars or the black dots are on the outside in both cases, and the oldest are sort of the green and red are on the inside. So there's good evidence for this happening, that these density waves come through and trigger star formation. I like to try to use spectra to understand galaxies, so I'm going to just talk a little bit about using spectra. Start with a beautiful periodic table of emission spectra of the elements. But what does the spectra of a galaxy look like? Well, the spectra of a star-forming galaxy looks like a mixture of stars of all different colors. So you have a continuum, that's this sort of smooth shape. And then you also have these emission lines that come from all of the gas that's in the galaxy that's around newly forming stars, that's being lit up and making emission features. And in particular, we have a lot of this H-alpha, which really correlates well with hydrogen alpha. It's a recombination line in hydrogen, correlates really well with star formation in galaxies. And other lines that can help you measure things to do with like how many generations of stars have been in the galaxy and stuff like that. If you look at instead of at a passive galaxy or a galaxy that's not forming stars, it's redder. So go here, it's got more emission down at the red end. Its continuum is tilted up, and it doesn't have those emission features. because it doesn't have any hot gas. It doesn't have any star formation going on. You can pick out, you're more likely to be able to pick out the absorption features that come from stars. You actually get those in the star formation galaxy too, but they're harder to see. And you get this really big break that comes from lots and lots of metal lines in cooler stars, and it starts to get accentuated when more and more of the light in your galaxy is coming from these longer-lived, cooler stars. So this D4000 break, or 4,000 angstrom break, we use as a measure of the age of the stellar population. See, it's weak in our star-forming ones and strong in these. Okay, so there's your spectroscopy of galaxies lesson. So now how are we going to do this? Well, we're going to use MANGA, which is a Sloan Digital Sky Survey, which is part of the Sloan Digital Sky Survey that measured spectra of galaxies. So I said the original Sloan did spectra of 1 million galaxies, and that's true, but it did spectra like this, one little optical fiber per galaxy. And for big nearby galaxies, that's missing a lot of the light from the galaxy, and you just get one spectra per every galaxy. So what MANGA did was make these bundles, hexagonal bundles of lots of fibers, and you get a spectra from each of these points. So now we get these little spectral maps of galaxies. So that's really interesting, right? And we can get spectra across spiral features. So this started in 2014. We now collected all of our data for 10,000 galaxies, and it's pretty complex data, actually. It takes a minute to get used to working with this. So you get a data cube. So at each wavelength, you can have a galaxy image, or at each point on the image, you get a full spectra. And then you can take out slices that are particularly interesting, like slices of H-alpha emission, or nitrogen, or silicon. You can use the Doppler effect to get rotation maps. You can use that D4000 break to get maps estimating the ages and all kinds of different properties. And we do it for a lot of galaxies. So we did this for 10,000 galaxies. There's actually more spectra than the original Sloan, because there are 10,000 galaxies and so many spectra per galaxy. And we did it for galaxies across the color magnitude. So we've got our red sequence and our blue cloud galaxies, all kinds of galaxies. So I think this is about a quarter of the total. This was a talk from 2018 by one of my colleagues, but I just really enjoyed his visualization. He put little images of the light coming through each of these hexagons for galaxies and made a little MANGA logo. And then we flick through, we get the hydrogen alpha flux, so that emission line flux for the same galaxies. The D4000, so the age of the stellar population. So MANGA, the word is disappearing. You get the velocity. You can actually do it separately for the stars and the gas, because you do it either on the absorption features or using the emission features. So you just all this just beautiful complexity. And there's all kinds of structure you can see in these maps. So this is a hydrogen alpha flux map, and you can see how the hydrogen alpha is linked with the spiral. This is equivalent width of hydrogen alpha, so it's kind of like the emission line flux divided by the continuum. So it's kind of like star formation divided by stellar mass. And you can see, again, it's picking out spiral structure. And I think this is D4000, and again, you can see the middle is older, and then you've got these younger regions where the spirals are. So it's really, really cool, and it's complex, and it's another example of a problem where computer algorithms struggle to automatically detect this stuff. I acknowledge they're getting better. But back in 2017, we decided we could use the galaxy zoom method to try to help with this problem, and that it would be really useful to have, for all of the MANGA galaxies, little masks or little kind of maps, basically, that tell us where the spirals are and where the bars are, and then we could pick spectra out from specific features. So we invited people to come in and look at the images of MANGA galaxies and draw onto them bars, foreground stars, so here's a foreground star, the center of a galaxy, in case there was more than one galaxy in the field, and also the spirals. And we did this, and we get things that look like this, kind of intensity maps of where different features are in a galaxy. So the orange here is the bar. We've picked out the stars, and we have the spiral structure. And you can use these in combination with MANGA data to pick out spectra from specific features. So you have to pick a threshold for your contour map. And I had a student look into this, and I think we decided this threshold was a good threshold. So here's Shuaib, who graduated in 2021, demonstrating that there is an excess of star formation rate in the spiral arms in MANGA relative to the inter-arm regions, which is kind of neat. So we published this work actually in the paper which kind of released these maps to MANGA. Yeah. Masha's a current student, and she's been doing this with stellar mass. So we're looking at actually the mass difference in the arms to the interarms. So again, we're actually finding there's definite evidence there are density waves with a sort of 20 to 30% density enhancement in the arms in the stellar mass. And Masha's working on publishing this now, and it's not true she's a sophomore, she's a junior now. Sorry, Masha. But she's doing very well with this. We can put these together and we can do specific star formation rate and other measurements, but this is still kind of a work in progress. And we're kind of moving towards trying to understand this question of the star formation efficiency changes, or if it's just, that's where the star formation is concentrated, which is interesting. And I was saying, Ben, I have students working on other projects to do with spirals, which I should totally have added, because there's all kinds of other interesting questions. So I work with a lot of undergraduate researchers. So they have a lot of related but slightly different projects. But we've been looking at gas content of flocculent galaxies compared to grand design and other things. And we're kind of adding little pieces of the puzzle of what spirals are and how they impact the galaxy that hosts them. But that's the end. I know I've been talking for a while, so I just wanted to say a big thanks to my undergraduate group and all of the volunteers at Galaxy Zoo, and thank you for listening.
Questions?
If you could see the dark matter halos, would there be as many categories of those as there are stars?
Well, that's interesting. That's a really interesting question. I mean, they would have a shape for sure. They're probably, I think we mostly think they're triaxial. They're much bigger than the images of galaxies I'm showing you, right? We think they extend much, much larger.
But there would be some sort of feedback, right?
Well, it depends what dark matter is, right?
Part of the visible morphology might be affected by the invisible morphology.
I mean, so bars, like the strength of a bar is related to the relative amount of mass that's in normal material and dark matter. And also whether or not that dark matter can accept angular momentum, which we don't know really yet, right? But if we assume it's some kind of particle, it should accept angular momentum. So there should be rotation in the dark matter halo. So in principle, you could have spirals in dark matter halos because they're rotational dynamic features.
Well, I was just thinking the other way, if some of the different types of galaxies are caused by different types of halos.
I mean, it's definitely true that there's mass dependence. So like elliptical galaxies tend to be in the most massive halos, and the really flocculent galaxies tend to be in lower dark matter mass halos. So that was another project I've had a student do, and you can see you're more likely to have grand design galaxies, and multi-arm, which are like grand design but more than 2 arms, tend to be the most massive galaxies, which we were talking about earlier.
It sounds like your feeling is that if you had sort of similar halos, that you could have very different visible spirals.
I think it has more to do with the gas content. So it might have more to do with not just the halo, but like how much material has, and like what's happened to the galaxy over time. I personally think these features do impact galaxies, but I think it's like a feedback thing. I think, what's happened to the galaxy impacts what kind of feature it has. But once it has these features, it will have a different evolution than if it doesn't have these features, because they do physical things to them in interesting ways, which is cool. I never really thought about spiral arms in dark matter before. It could be.
Well, I know that how concentrated it is in the very center is in a rotation curve is sort of the hardest thing to constrain, but also the most interesting thing. And so basically whether or not they were cuspy or core,
Yeah.
I think the cusp wars. So it's let's just say a very contentious thing. So we don't quite know. Very likely to have something like that, but I think dark matter is a little more pressure utilized. So small, like a spiral structure will dissipate faster.
But
again, it comes down to what is it.
yeah, and if you come back to, I only have like a toy rotation curve here, but we can measure this for a lot of galaxies. And so I think there's some evidence that the pitch angle of the spiral has to do with the gradient of the rotation curve. And so that's to do with the shear between concentric rotating circles. So if there's too much difference in velocity between, this ring of stars and the next ring of stars, you're going to have a different pitch angle spiral than if they're more comparable. And those kind of shape, like the shape, this rotation curve is basically dominated by dark matter, right? So the dark matter says this. Kyle?
You had, sorry, I'm picking out a small point here, but you had a picture where you, or a plot where you placed the Milky Way kind of in the Green Valley. And on that figure, I thought I had seen what looked like a small arrow. Was that an indication of what we thought motion through the Green Valley might be for the Milky Way? Or is that pointing to one of the stars?
You know, I got no idea. We'll have to go to this. I think this figure is from Fielder et al.
Okay.
I don't remember. I am a co-author on that one. But I don't remember what the arrow is for. I'm sorry.
No, that's fine. I was just curious because if it...
Oh, it looks like it's the difference. It's something to do with the assumption of the inclination. So if you saw it very face on versus much more edge on, B over A is the axial ratio.
Right.
So I think it's, yeah, I don't remember, sorry. Yeah.
But if it's implied motion, that would be interesting to me because then that would kind of give an indication that, at least in this paper, that the Milky Way was rejuvenating. And then my question from that would be, then what would be causing that?
Yeah. It doesn't look like motion to me. If you look at the legend, it looks like the difference is really an inclination thing. So I think it's just like...
I see what you're saying. Yeah.
It depends. The color that you would see the Milky Way have depends a little bit on its inclination, which in fact is the paper that Ben had read that I wrote, was about how the colors of galaxies change with viewing angle. So we typically either try to, for this kind of work, we either try to just limit it to face on or try in some way to correct the color for inclination effects, which is a statistical correction, right? Because we don't actually know, but yeah.
This may be a dumb question. What does inclination for the Milky Way actually mean?
So this is like, where would, like if we were an alien race, like a long way away from the Milky Way, what color would we think the Milky Way would have?
So this is, okay.
So it's saying that depends on whether we're an alien race that lives that way or an alien race that lives that way.
So it's playing with the idea of viewing angle.
Yeah.
Okay.
What's the highest redshift that we've actually observed spiral galaxies in?
Well, that's a great question. I think there's some redshift 1 or 2 spiral galaxies. They tend to be the most massive ones, and you find like 1 or 2. That's the first question I looked at in the JWST imaging, and so I've been working on a paper on that. And there's a couple of like redshift 2 or 3-ish spirals.
Yeah, so I was just wondering, at what point in the history of the evolution of the universe spirals start to form?
I mean, so that's one of the cool things that JWST is revealing. We think a bit sooner than we thought. So we got to like figure that out because the spirals, galaxies seem to get organized a bit earlier than we thought they should.
Is there a minimum mass that a galaxy has to have to display spiral structure?
Also a great question. There are some dwarf spirals. There's a dwarf spiral category. So, but they tend to be pretty rare. So most dwarfs are elliptically looking or very disorganized looking. Yeah, you asked me questions about like outside of the parameter that I typically work in, because there's typically work in this Sloan sample, which is really nearby and pretty bright galaxies, but they're great questions. Trevor had a question.
So you had a plot with the correlation between like couples, and you were trying to find if they correlated or not. You only did like the galaxies. You only had like nearby galaxies. Would that change if you did farther galaxies?
I think that'd be a really interesting thing to test, right? So, I mean, galaxies, we picked that redshift range to make it something called a volume-limited sample. You'll probably find it quickly, hang on. Yeah, I don't really have a plot that demonstrates it, but basically we wanted to be able to see all of the galaxies at any redshift in the volume so that we weren't being impacted by the fact that the low mass galaxies we could see nearby, but we could only see high mass galaxies far away. So you set the limit, the stellar mass limit to 10 to the 9, so 1 billion solar masses, because we could see 1 billion solar mass galaxies at the highest redshift. And the redshift here was kind of conservative, but you want to be sure you can really see spiral features, right? So you don't want, as galaxies get further away, it gets harder to do that. But you could definitely ask the same question with the JWST data once we have enough galaxies to look for correlations, we could ask that question for much more distant galaxies. These are all much further away than Hubble's sample. Hubble's sample tend to be like way too close, like too much in your face for the type of science I do.
Any questions from not me? Because I have a list.
Wait, this is where you want to have dinner tonight.
Okay.
Jerry?
I have a question. We tried a few years ago to do some crowdsourcing galaxy zoo type stuff on spectra. You know anybody who works on spectra successfully with crowdsourcing?
So spectra are a little hard because they're a little harder to explain, and it's a little harder to motivate what's interesting. So crowdsourcing projects work really well if they have a pretty low barrier to entry, because then you can get a lot of people involved pretty quickly. We have had some spectra, so Galaxy Zoo worked really well, and I didn't talk anything about this, but my colleague Chris Lintott, who was one of the people in the pub originally, got really into the method and launched something called the Zooniverse, which is now enormous, much bigger than Galaxy Zoo. We're now a part of the Zooniverse. And the Zooniverse runs, I don't know, several hundred different crowdsourcing projects that use this technique. So the Zooniverse has hosted spectra-related projects, I think. I don't know that any of those have really been big. What has been big is looking for exoplanet transits in light curves, which to me is a bit like, it's data, it's not an image.
Time instead of wavelength.
Right? A lot of people said, Galaxy Zoo works because galaxies are pretty, so people like to look at them. And I think there is a part of that there. But all of the volunteer surveys we've done have really pulled out the primary motivation is they want to help us with science. So we take really seriously, A, you say thank you because they're volunteering their time to help you do science. B, you do science with it. You don't collect it just for fun and then not do anything with it. I'm sure there's more. I should go with 3 next, right? So, and the planet hunters and exoplanet, all of the looking for transits, so looking for a little dip in light when a planet goes in front of a star, have gone really well because it's really cool. You want to find a planet. You might find a planet and have it named after you and stuff. So if you can motivate the spectra, like what you want out of the spectra really well, then there's no reason it shouldn't work. I just haven't seen it done yet really well. Oh, I remember what C is. You shouldn't ask them to do something that's easy to do with a computer, which is getting increasingly hard to convince people of. But and I didn't talk about Zubot at all, but now we have Zubot in the loop. So machine learners got a lot better at galaxy classification, particularly telling the difference between elliptical and spiral. Honestly, we can do that now with the machine. And so we have this thing called Zubot that goes through and does that, and then leaves the more complicated stuff for the people, and also gets trained kind of in the loop. So turns out your machine learner is going to work a lot better if it's trained on the actual images that you're asking it to classify. And so we kind of, you do 10,000 images and you train the machine and then it does the really easy ones and it pops back out the things it's not sure about. So it's a Bayesian CNN, so it does a classification plus a certainty level on the classification, and anything where it's uncertain we send back to people and then we sort of train it again. This is very much a royal we. I do not do this work. My colleague, Mike Walmsley particularly, is the lead for this in Galaxy Zoo, and there's all kinds of cool stuff with Zubot.
Let's thank our speaker again. Very good.